Okay, hello and welcome everyone. Today is the first day of Carbon Sequestration Week, and today we're going to be talking about engineered carbon capture and storage. We have two amazing panelists who will be introducing in just a moment, two experts in this field. And then my name is Brian Stewart from Electrify Now, and Joe Wachunas, and I will be hosting today's episode and answering, managing the chat, that sort of thing. But we'll turn it over to our panelists in just a minute. I wanted first to just kind of give you a little introduction in case you're unfamiliar with Electrify Now. We're a voluntary organization working to help people understand kind of how to think about the importance of our energy networks in the problem of climate change and how all of us are part of that system and all of us can take actions to create a clean energy future. We talk about three steps to take in your own life, which is about cleaning up your electric supply, getting clean energy to your home, and then getting rid of anything that burns fossil fuels in your home. There's excellent electric alternatives for every one of those things, electrifying your transportation. And then the fourth thing we talk about is making sure we don't leave people behind in this transition, especially low-income people and BIPOC communities who oftentimes are the last to transition to these newer and better technologies for home power. And so there's things you can do with using your voice, and also donations that we have some information about to help make sure that that community transitions at least as quickly as the rest of us, if not beforehand. There's tons of information on our website about all these topics, tips, resources, discounts from suppliers and contractors, et cetera. So lots to check out at electrifynow.net. I also want to give a quick shout out and thank you to all of you who have donated to Friends of Trees. What we do every time we host one of these webinars, we have a charity organization that we ask for donations. In this case, it was Friends of Trees, who's an amazing organization here in Portland, who's responsible for helping improve and grow the urban canopy that we have. We're fortunate to have one of the cities in the country with the largest urban canopy, and it makes a huge difference in terms of livability in the city. And partly that's due to the great work from Friends of Trees. So thank you for your donations, and anyone else who's motivated to give a few dollars in thanks, please check out Friends of Trees.
All right, great. Hi everyone. I'm Joe Wachunas, Brian's teammate at Electrify Now. So excited to be here. Today is day one of Sequestration Week. And why do a week on carbon sequestration? If you're familiar with Electrify Now, normally we educate on ways to reduce emissions, because that's an enormous problem facing us. Something to the tune of 50 billion tons of carbon a year we need to stop emitting into the atmosphere. And so we like to educate on how to do that. And to us, one of the most straightforward paths is to electrify everything, to use clean, renewable electricity to power our cars, our homes. And that's a really simple and straightforward path to reducing our emissions. But we know that there are certain sectors and industries that are really difficult to electrify. Our panelist today, Brett, will be talking about the cement industry, as well as plastics and fertilizers. And so these are difficult to just use electricity in these industries. And even when we get to zero emissions, this really difficult challenge that we're facing, we also know that we're still going to need to sequester or take some carbon out of the atmosphere and store it. The Intergovernmental Panel on Climate Change says that in one of the pathways by 2050, we're going to need to sequester something like 7 billion tons of CO2. Deepika, who's a panelist today, will be checking my facts in just a second, and store it. And that's more than the United States, the entire United States emits per year, just to give you an idea of the context. So we felt that it was really important to talk about sequestration, and there are a lot of ways to sequester or capture carbon out of the atmosphere. And so every day this week, we're going to be looking at a different way. Today, we're going to be talking about carbon capture and storage, which is using machines to take carbon out of the atmosphere and from smokestacks and then storing in the ground. But there are ways to do it, obviously, with forests, grasslands. We're going to be exploring cement and concrete on Thursday, and soils on Friday. So just a lot of great ways. And we are so excited by the interest that this week has created. We have over 1,800 people registering from 41 different countries. So welcome to everyone who's here today. If you want to say where you're from, go ahead and write it in the chat. We'd love to hear where you're from. We're based in Oregon, but we want to hear where everyone else is from if you're interested. So quick housekeeping notes. If you'd like to ask a question, please put it in the Q&A or the chat box below. We will get to as many questions as possible. And go ahead and submit them there. We'll do a couple presentations and then get to Q&A at the end. And so let me, without further ado, introduce our panelists for today. Deepika Nagabhushan is a program director from the Clean Air Task Force. She leads efforts to make carbon capture, utilization, and storage technologies widely available globally by mid-century. She works across policy, regulatory, and market-based areas related to carbon capture and storage. And she'll be going first with our first presentation. And then we'll hear from Brett Henkel. He's the co-founder and VP of Svante. Svante is a clean tech company with a vision to be the global leader in building a CO2 marketplace. He was instrumental in creating the process and the hardware used to prove Svante's carbon capture technology. He'll be talking about some of their demonstration and pilot projects. So without further ado, why don't we stop sharing screen and we'll turn it over to Deepika. Go ahead.
Thanks, Joe, and thanks, Brian, for having me. I'm very excited to be here and to know that there's such an interested audience. I'm just going to quickly share my screen. There we go. Okay. All right. Without any delays, I might just jump in. So hi, everybody. As Joe said, my name is Deepika Nagabhushan. I am the program director for the CCS program at the Clean Air Task Force. So just a little bit about Clean Air Task Force for those who might not be familiar. We are just over a couple of decades old. We were founded in Boston. We're relatively small for an environmental NGO, but we're feeling very blessed to have a budget of about $15 million. And we're mainly funded through philanthropy. Our mission is to lead the way to an affordable zero carbon energy system through pragmatic policies, business strategies, and technologies, and sort of meet the climate goals. And how we do that is through policy development, policy advocacy. We engage in legislation and rulemaking. We also engage in education and outreach across stakeholders, whether it's policymakers, administration, private sector, and other NGOs as well. And we sort of operate in a collaborative way. So that's a very brief introduction of Clean Air Task Force. You can find more about us on our website. What we'll cover today is just a little bit of an overview. We'll talk a little bit about why CCS is essential to meeting our mid-century climate targets of being net zero CO2 emissions. And we'll talk a little bit about what we know about CCS deployment so far, where it is, what's happening right now, a little bit about the technology, a little bit about the storage. And we'll talk a little bit about the policies that we have currently and what the policy pathway forward would look like according to Clean Air Task Force to get us to where CCS needs to be in order to play its share of the role in meeting the climate targets. All right, so CCS, why CCS is essential. You're going to see sort of interchangeably using CCUS and CCS. They're practically the same thing. It's just there's just too many words. So CCUS basically is carbon capture, utilization, and storage. And CCS just drops the U, but it kind of sometimes also is used in the space where you're still meaning to say utilization, but it's the same thing technically speaking. Global, so I always like to start with like a really high level point, and this is an IPCC image that I'm sure many of you in the audience might recognize. Basically, the IPCC model says that we need to get to net zero by 2050. And it doesn't entirely mean zero emissions. It means net zero emissions by 2050, but the model does reach zero emissions by 2060. So it's not like you can get away with not getting to zero emissions, but you just have an extra decade over there to sort of get to zero, but continue to do negative emissions at the same time. So this is to avoid overshoot beyond 1.5. And what the modeling says is, out of the 4 scenarios that the IPCC modeled, you'll see that 3 of them use extensive CCS, ranging from 300 billion metric tons cumulatively stored by 2100 to over 1 trillion metric tons stored cumulatively by 2100. There is one scenario that does not rely heavily on CCUS, but it does happen to have much less energy usage globally speaking. So the point I'm trying to make in this slide is basically that CCUS is an essential technology, because without that, it's sort of a risky trade-off to try and pursue just one pathway in which you're trying to cut energy usage globally, where already more than 1 billion people do not have access to modern energy today, and they will have to get access. And so pursuing a pathway where we're trying to cut from the demand side is going to be a risky bet. So it just makes sense to have this tool in our toolbox. CCS, I don't know if, again, this is something, I just want to make sure that everyone's on the same page as to sort of what CCS is and where it goes. And the truth is, CCS can be applied across sectors for decarbonization of any of these sectors that you see on the screen. In terms of transportation, CCS can be utilized to make clean fuels, clean liquid fuels like hydrogen or ammonia that can be used for decarbonizing shipping or heavy duty transport. It can make biofuels that can decarbonize partially any liquid fuel that we use today. And of course, electrification of light duty vehicles that could also be powered with electricity that is made from fossil fuels, but the carbon is captured and stored. And industrial sector is very important because it's one of the unique sectors where CCS plays a very unique and essential role, especially because industrial source sector does not only have emissions from fossil energy use, but it also has emissions from just chemistry, like heating up limestone to make cement makes CO2, and it has nothing to do with electrification or anything to do with fossil fuels. So there are a lot of these situations, such as similarly in steel. And so CCS can capture those emissions and store them. For heat and electricity for buildings, same thing. You can electrify, produce power, clean power through CCS on fossil-fired power plants. We know that there's ability now that to remove almost 99% of all CO2 from electrical power generation plants. And of course, in the end, we have carbon removal, which I think Joe was referring to in his introduction. Direct air capture, ocean capture, or bioenergy with carbon capture. All of these are mechanisms to remove CO2 from the atmosphere and put it away outside of the carbon cycle. This is just an image to sort of give you a vision of what a net zero energy system looks like. And this is how we envision the net zero energy system in the future at CATF. On the top line, you'll see all the end uses of energy, whether it's buildings for heat, lighting, transport, and there's industry. And then at the bottom line, you see primary sources of energy, whether it's sun, wind, or nuclear, or fossil fuels, but with CCS. And all these energy sources deliver energy via the middle row, which is either zero carbon electricity or zero carbon fuels. So this is how we imagine the net zero energy system, in which, as you can see, CCS plays an important role if we still have fossil sources as part of our energy mix. So here's a slide that just talks a little bit about hard to abate sectors that Joe was talking about. On your right-hand side, the pie chart is sort of all of the emissions globally. The little pieces that have been pulled out are the ones that constitute what we term as hard to abate sectors. So we've got aviation and shipping and transport. We've got load following electricity, or in other words, firm, clean electricity in the power sector. And of course, we have in purple and blue, we've got pieces of the industrial sector like cement and steel, which I was talking about, which have emissions that have not much to do with fossil energy, but it's just part of the chemistry itself. And these are sources, so they make up 30% of all emissions that will probably need to rely on carbon capture and sequestration as a decarbonization pathway, specifically the iron and steel and cement industry. I know Brett is going to talk a little bit about that in his slides. And they form close to 10% of emissions globally. And as you can remember, we have got to get to zero. We can't let these be. Okay. Now that we've spoken all about the sort of where CCS fits in the net zero world, I just want to quickly take a step back to talk a little bit about the technology itself for those that might not be very familiar or in the weeds about within carbon capture. The first thing I would like for people to take away from this is that carbon capture technologies are not new. We have been using these technologies in the gas processing sector for decades now. So it's not something that has not been understood, it's just not been used for climate purposes. And carbon capture technologies are not, it's not one single technology, it's a suite of technologies that include categories, like 3 categories mainly, capture, transport, and utilization or storage of CO2. And each of these categories have various kinds of technologies. There's post-combustion capture, and there are technologies that use solvents, some that use sorbents, some that use membranes. And then there's direct air capture, which is a different kind of technology in itself, or carbon removal technologies that can take CO2 out of ocean, water, or biomass combustion. And transport could be pipelines, truck, rail, shipping. It could be in any way, depending on where it's going to and from where. And utilization, it can be when CO2 is utilized to convert it into a product of commercial value. It can be converted into fuels. You can mix it with hydrogen to make synthetic fuel. Or you can use it as an injectant for enhanced oil recovery, which is a big market for CO2 when the oil prices are high enough. You can sell it to food and beverage sector for carbonation and other purposes. And of course, you can store it permanently in geologic sites, which is what we'll talk about a little bit more today. Innovation is underway in all of these areas. And the other thing about the business model of how this will be deployed is that it does not have to mean that the person that is capturing must also transport, must also utilize or store. It's sort of a value chain that sort of gives way for a carbon management industry to emerge, where each piece is owned by a different private sector and can all come together to provide carbon capture and storage as a service. So it's just not one single technology. That's one thing I wanted to take away. And here's a little bit about the storage itself. This is an image that sort of shows how deep CO2 would ideally be stored. It's typically a mile deep. That's about 4 Empire State Buildings, way, way, way deeper than where our drinking water aquifers lie. And usually these sites are very carefully selected after studying, and they're known as saline reservoirs. Basically, it's deposited over millions of years, tens of millions of years or more. They are porous formations, mainly sandstone, I would say. And on top, usually you would find multiple or maybe one or more layers of impermeable rock layers, which act as seals or are known as cap rocks. They are usually impermeable. So this porous formation lies underneath with impermeable layers above. And when you inject into the porous formations, the CO2 gets trapped in those pores. And that is the primary mechanism through which we achieve storage of CO2. And the layers that I mentioned above are the ones that prevent the CO2 from rising back up into the atmosphere or into any drinking water aquifers. So these are criteria using which people select these sites. US has regulations that's almost a decade old now that sort of ensure site selection is right, measuring is right, and there are lots of parameters that operators have to follow, which ensure the permanence of CO2 that is stored. And I want to touch upon 2 things here. There are incentive programs in the US currently. There's 2 main ones. that I want to talk about, and both of those require that these regulations are followed, and there's a lot of verification involved. And so if a project falls under these programs, then we can rest assured that they are following these rules and that they are achieving permanent storage. So one is 45Q. It's a tax credit that was passed in 2018, and it's a federal tax credit. It gives about $35 per metric ton for anyone storing CO2 via EOR or utilization, and $50 a ton for anyone permanently geologically storing CO2. So that's at the federal level. And at the California level, there is, it's the only state that has a carbon capture credit, carbon capture incentive program, which is under the low carbon fuel standard, which provides close to $200 a ton of a credit if a project follows what they call the permanence protocol, which is basically, again, a set of regulations for site selection and monitoring. CCS has been deployed extensively in the US. We have about 5,000 miles of CO2 pipelines already, but this is what I was saying earlier, none of these projects were implemented for climate purposes. They were implemented for commercial purposes, which happens to be CO2 being taken from either natural sources or industrial sources and taken over to oil fields for what we call enhanced oil recovery. But this does mean that the industry has a lot of experience doing this. We have examples in the power sector, the Petronova plant, currently mothballed for business, for economic reasons. And we have a power plant up in Canada, Boundary Dam, from both coal-fired power plants. We have ethanol project in Illinois, Decatur, storing 1 million tons of CO2 per year into saline, in a saline site. We have we have 2 hydrogen production projects. We have some examples of industrial CCS outside of the US. There's upcoming projects on steel in the Middle East, and then there's one in Australia capturing from an LNG facility. These are all, and there's more. There's about 18 large-scale projects that are operating across the world right now. And because of 45Q that I was just talking about and the California LCFS, we are actually seeing a new wave of projects being deployed. And these are all early stage projects that you're looking at on this map. This is a map that Clean Air Task Force released last year, and the link is on the slide. If anybody wants to look at it, it's an interactive map. You can click on each of these bubbles and look at information about these projects. There's actually more than 35 now already in the pipeline. Many are in early stages doing feasibility studies, but some are close to financial close as well. And here, I don't know if you can see my arrow, but the one in Colorado, the blue dot, is Brett's project that Brett is going to talk about in just a few minutes. This is just to sort of show the kind of momentum we've had with just one incentive or two incentive programs, which is really telling in terms of the momentum we have for policy and for deploying this technology. I also want to touch upon negative emissions or carbon removal. I'm very sure that many in the audience have a question around what Elon Musk's prize was about. So I thought I'll touch upon this a little bit. There's a lot of voluntary actions that some companies are taking, not because it's regulated, not because it's they're making money off. It's basically what they think is required for them to be a leader in this space. And to contribute towards advancement of technologies that are essential for meeting climate goals. So you see examples like Microsoft, Shopify, Stripe, Volkswagen, United Airlines, all investing in either direct air capture projects or in companies that are doing different kinds of removal, whether it's ocean capture or bioenergy carbon capture. And Elon Musk recently announced a prize of $100 million for R&D. So for really early stage bench scale ideas so that those can then be scaled up. Both areas of investment are important. We definitely don't have any direct air capture project at scale today anywhere in the world. So we're still yet to see a big project happen. There are some underway. But any investment, whether as a customer of credits or whether as like Elon investing in supporting early R&D, are all very important areas of investment today. So many people ask, okay, so we have 45Q, we have all these 30, 35 projects in the pipeline. So what now? What do we need to do now? And the answer to that question really lies in sort of understanding the economics of CCS a little bit, and sort of just understanding the various ways in which we'll need to incentivize this entire sector. The short answer is the 45Q is not sufficient for wide-scale commercial deployment of CCS. It might be enough for projects in some specific sectors, but not across, because it costs different amounts of money to do CCS in different sectors, and that's driven by a few things. One of them being CO2 concentration. And on the right-hand side, you'll see a table. I just made that table just to sort of identify various sources where CO2 can be captured from and how the concentration of CO2 differs so widely. In an ethanol facility, you can get CO2 at 99% concentration. Basically, you don't have to do anything except compress it and then send it wherever you need to send it. So it's a lot less expensive, relatively speaking, versus different kinds of sources like steel or cement, where the concentration of CO2 is much lower. Think about air. Air is literally the least, which is 0.04% of all molecules, and it's just harder to capture that because it's such low concentration, which is what drives some part of the expense that we'll have to bear. Which is why only some applications will sufficiently incentivize CCS application, but not all sectors. And this is why we at CATF, believe that we have sort of a theory of change as to how we will need a whole range of policies to pass, so to enable application of CCS across these sectors, across the range and spectrum of costs and difficulty. I guess it's not just the concentration. There are lots of other engineering issues that come up. We think that we first need the government to support R&D, provide demonstration grants, not just one of a kind, but potentially third of a kind, all the way to third of a kind deployment or fifth of a kind deployment. We believe that there need to be support through loans, grants, and those kinds of things. And in addition, we think that 45Q needs to be modified to suit some of the needs of the applications. For instance, CCS on gas-fired power plants will require just a little bit of an addition, such as in the form of something like a production tax credit, so $1 per megawatt hour, additional to 45Q that we already have, that can enable CCS on gas-fired power plant to be economical. We obviously need also the ecosystem to develop. Where does the CO2 go after it's captured? Where are the pipelines? Where will it go? Where are the geologic storage sites? These are all things that government investments can spur a start in. And on the right-hand side, you see how at a point when deployment can help costs of these technologies to come down, we can then use economy-wide policies like carbon pricing, clean energy standards, emission limits to drive wide-scale deployment. And the graph in the middle kind of captures an older figure of what we learned from the IEA 2-degree scenario. We no longer want to aim for 2 degrees. We want to aim for higher than that. We want to aim for 1.5. But even the 2-degree scenario in the US sort of ended up capturing close to 200 million tons a year by the year 2030. So we're about 10 years away from that point, and we have to get to 200 million tons a year, and we are at pretty much like 1 or 2 single-digit numbers at this point. So that's the distance we have to cover, and this is the policy pathway that we believe can get us there at CATF. And with that, I will close out and see you in the question and answers section. Thanks, Joe.
Great, thanks, Deepika. Thanks so much. And there's already a really robust chat conversation. Folks, we encourage you to keep asking questions in the chat or the Q&A, and Deepika and Brett will get to those when they're not presenting. But without further ado, I'll turn it over to Brett for his presentation. Then we'll get to live Q&A at the end.
Brett, you're on mute.
Did my slides come up? I don't see them, Joe.
I don't see them either. It looks like you're at the end of your slideshow.
Ah, sorry about that. That makes sense. Okay, thank you very much for inviting me to present here today. My name is Brett Henkel. I am co-founder and vice president of strategic accounts and government affairs at Svante. We are developing CO2 capture technology, and we are targeting industrial emissions. So thank you very much, Deepika, for an excellent introduction to my presentation. That was wonderful. So a little bit about Svante. We are 80 employees right now. It was founded in 2007, so we've been working on this CO2 capture technology for quite some time. We are excited to announce that we just successfully closed a Series D round of financing of $100 million US, which to our knowledge is the largest single financing for point source capture globally to date. So we're quite excited about having the ability to finish commercializing and providing this this important tool to the world for to use for GHG reductions. Okay, what I want to start with is where we're focused on applying our CO2 capture technology. In the last 20 years, transportation, the combustion of fossil fuels for transportation and electricity has taken a lot of the brunt of focus on reducing CO2 emissions. And there is quite a few options in that space that are making very, very good headway, one being electric vehicles and fuel cell vehicles, and in the electricity production space, renewables of all forms have made fantastic headway on reducing GHG emissions in those sectors, and we all are huge fans of that work. I own an electric vehicle, and I'm a big fan of fuel cells and of all renewables too. What has been under the radar is really the industrial emissions, and just let me start here. And this is less well understood, especially by the public, but I would say by everyone really on industrial emissions. It's a little bit harder to figure out where the CO2 comes from, and I must say it's much harder to figure out how to stop the CO2 that's being emitted from industrial emissions. So some examples that I use that really relate to everybody in their everyday lives is I like to talk about four things. Concrete being the number one. We build our modern cities with concrete, and concrete is made with cement, and that's a big one of the big industrial emitters. Is concrete. So it's hard to imagine a world without concrete right now, since we're so dependent on it. I believe the concrete industry says it's the second most used product in the world after water. So very dependent on that, and a big CO2 footprint. The other one is steel. Steel is such a wonderful product that we use in so many different ways. It has a footprint. And plastic is we use it every day. We rely on it, and it has a footprint. Plastic comes from fossil fuels, and the production of plastic actually emits CO2 as well. And the last one I like to talk about is fertilizer. We feed our population, global population in the world, with fertilizers that are based on fossil fuels. So why I'm pointing this out, it's not just the obvious things that produce CO2, it's really things that touch every day and all of us. There's no one that isn't touched by these products and the industrial emissions that they produce. So that's where we're really targeting our technology. We are developing CO2 capture, and I like to explain what CO2 capture means. When we talk about CO2 capture, what we're really saying is that we take flue gas, which is a mixture of CO2 and nitrogen mostly, and it's quite useless. That's why we put it into the atmosphere. It has between 2% all the way up to maybe 25% of CO2, and the rest is nitrogen, and then there's usually some contaminants in it as well. And it is, we don't know what to do with it. So that's why it goes into the atmosphere. Now to deal with the CO2 in it, because it's the CO2 that is causing climate change, we have to purify that CO2. And that's what CO2 capture is from our perspective. It's purifying that CO2 in order for us to sequester it, to trap it so that it doesn't go into the atmosphere. So what Svante is doing is taking the flue gas, and we're processing that flue gas and making pure CO2 using a novel technology that I'll get into in a minute. Now, once that CO2 is purified, a pure form of CO2, there's many different pathways of making sure it doesn't go into the atmosphere. So one that I think even in the chat here, there's a lot of people talking about. A good example is CO2 being injected into concrete. It's a fantastic way of trapping CO2, and it's being worked on and developed, and the CO2 stays in that concrete forever. There's other ways of CO2 conversion too, into all sorts of carbon products. There's also, Deepika touched on this, is combining CO2 with hydrogen, with clean hydrogen, and we could make liquid fuels so that we don't have to burn fossil fuels in the transportation sector. So that's a pathway of reducing CO2 emissions. And then there's one that is definitely more controversial, but I would say from my perspective that it is necessary, and it is proven, and it is a viable pathway for storing massive amounts of CO2 that we produce, geological storage, storing it underground. Now, this also has another piece attached to this. In the past has been CO2 being used for enhanced oil recovery. And I must say that has never been the driver is to capture CO2 for enhanced oil recovery. The driver has been the sequestration of CO2. It's just that enhanced oil recovery gives a revenue stream that didn't exist. It didn't exist before 45Q and other regulatory frameworks are in place to make economically viable to capture CO2 and store it. So enhanced oil recovery was just a mechanism to start these projects, to get them off the ground, to provide a revenue stream to start doing that, okay? Now, a little bit about our technology. Our purification of CO2 technology is based on a new material called an adsorbent. This new material grabs onto CO2, it lets nitrogen pass through. It doesn't grab onto the nitrogen. So when a flue gas is passed through this material or close to this material, the material will trap all the CO2, okay? And it'll let the nitrogen pass. The nitrogen can go into the atmosphere. That's all right. But now we have the CO2. We then use low pressure steam to release that CO2 in a pure form, okay? Now we have the pure CO2 that we can do a lot of things with to make sure it doesn't go into the atmosphere. We take this material, we put it into a machine called a rotating adsorbent module. It turns a batch process and turns it into a continuous process that can be connected to a flue gas. Okay, so the flue gas goes into this machine continuously. Nitrogen is coming out one end, and on the other end, pure CO2 is coming out. And this pure CO2 can then be used for, like I said, the three things: conversion, or it can be used to make liquid fuels, or it can be geologically stored underground. Okay. The competitive advantage our technology has is a lower capital cost. Everyone wants CO2 capture and that entire value chain to cost less, because what I like to make the analogy of is that, hundreds of years ago, we used to release our sewage into the street even, or into the nearest river right beside us. We figured out that wasn't very healthy for the environment or for us. It's not very much different for CO2 and flue gas going into the atmosphere. It is a pollution that we have to stop doing, but there's a cost associated with it, right? So we all want that cost of capturing that CO2 and making sure it doesn't go into the atmosphere. We all want it to be less cost, right? Then it can be deployed on a bigger scale and faster. Okay, so our technology brings to the table a lower capital cost option. The systems that are in place right now that you would see, there's quite a few worldwide, are based on a liquid amine technology. 2 very, very large towers are needed for this technology. It's quite capital intensive. Our technology it's one machine that does the job. It's a fairly short machine because it's only 1 meter tall is the adsorbent. There's ducting and whatnot that has to be attached to it, but it's fairly short. So it's a compact piece of equipment. So the capital costs, we're targeting a 50% less in capital cost. And this will allow more, economic deployment of CO2 capture technology. Our projects that we have so far we have our flagship project in Saskatchewan with Cenovus Energy. We are connected to a natural gas steam boiler. This is a 30 ton per day capture plant, or a 10,000 tons per year. It's been running since end of 2019. We're having really good success with it, and we're we've made the transition from the lab, developing technology in the laboratory, to an industrial setting and proving it can work in an industrial setting. We are also working with 2 projects with our key partner, Lafarge-Holcim. We are working on one project in Richmond, British Columbia here on a technology development project. I'll touch on that a little bit more. And then our flagship project in Colorado, which is a commercial plant that we're working on, that I'll touch on more. So our project in Richmond here in British Columbia is a 1 ton per day plant of CO2, so fairly small, but we're proving that our technology can deal with the contaminants in cement flue gas. There's SOx, NOx, oxygen, and particulates in cement flue gas. We have to prove we can deal with that. We have to prove that we have the most economical CO2 capture technology. And an interesting feature of this project is that we're also demonstrating a utilization of the CO2 as well. Here in the Lower Mainland in British Columbia, there's earthquakes, so we can't put CO2 under the ground for geological storage. And so we're demonstrating CO2 being injected into concrete with partner companies, Solidia Technologies, Carbon Cure, and Carbon Upcycling, all putting CO2 into concrete in one form or another to make sure it doesn't go into the atmosphere. Now, our large scale capture program happening in the United States, in Colorado, is the Lafarge-Holcim cement plant in southern Colorado near Pueblo. It is a very large plant. It's about 5,000 tons per day of CO2, or 1.5 million tons per year. We are in the engineering phase, the second engineering phase of that. It's being sponsored by the US Department of Energy. It's got a wonderful consortium that's working on this technology. Total is a sponsor. They are also working on putting in possible a solar plant to provide clean electricity to the capture system. We have Kiewit as the engineering firm and the construction firm that would be actually designing and building the entire balance of plant of the capture plant. And remember, Kiewit is the EPC firm that built the largest capture plant in the world being the Petronova plant in Texas. And we, of course, Lafarge Holcim is the emitter. And we have the key piece of the puzzle is always the off-taker of the CO2. This CO2, this cement plant happens to be within striking distance of an existing CO2 pipeline owned by Occidental Petroleum. And this CO2 pipeline will take CO2 into the Permian Basin for sequestration. Now that can be tied to enhanced oil recovery, yes, to provide a revenue stream, but more and more the shift is to pure sequestration. The 45Q tax credit that Deepika talked about provides $50 a ton for sequestration alone. So there's a revenue for players and consortiums such as these to actually do the sequestration and make it economically viable. Okay, so this is a very exciting project that would be upwards of the largest capture plant in the world, and would certainly be the largest capture plant in the world on cement manufacturing. We also have a second pilot project that are happening with Chevron. We get another kick at the can to do another pilot plant. We're incorporating all of our lessons learned into this pilot plant. It will be deployed in California, just outside of Bakersfield, Chevron. It's also connected to a natural gas steam boiler, and it's being funded by the U.S. Department of Energy contributions, and is being designed and the balance of plant being built by Kiewit as well. This should be operating at the end of this year or early in first quarter of 2022, and will really showcase our newest and latest CO2 material that we're developing, the CO2 adsorbent material that we're very, very excited about. We are also playing in the direct air capture space. We believe that direct air capture is also needed. The legacy CO2 that's in the atmosphere already is staggering and has to be dealt with. Now, of course, capturing CO2 from the air is more difficult. It's only 400 ppm in the air itself, so it's a bigger technical challenge, bigger economical challenge too. But we were working in this space by partnering with Climeworks, who is a Swiss-based direct air capture company, and we're providing our technology to help reduce the costs of direct air capture. We have a program in the United States working with Climeworks to demonstrate our technology with Climeworks technology, and that's also being funded by the U.S. Department of Energy and will be deployed in California as well. Our business model is to be a technology provider. This is an incredibly complex endeavor. We want to supply the structured adsorbent and the active material and the machine that actually does the work. The rest of it will be handled by engineering firms and the emitters themselves to do the design of the balance of plant, the design of the compression train, if there's a pipeline needed, or utilization will all be handled by partner companies or the emitters and EPCs themselves as well. So we wanted to provide this technology to the world so that it can be deployed in many, many different sectors and by many, many different companies. Our first target is North America. We believe because of the infrastructure that's already here, that the CO2 pipelines that are here already provide an early term kickoff point for CO2 capture and sequestration. So we're looking at for the major regions in the United States and Canada, one being in California. There's so much momentum happening around CO2 reductions in California, the Permian Basin with all the pipelines, the Gulf Coast. There's so much industry there. There's already CO2 pipelines. And of course, in Western Canada, we just finished building a CO2 pipeline in Alberta that costs upwards of $1 billion. and it's mostly empty right now. So everybody wants to fill that pipeline and make sure that we can maximize the infrastructure that we have in place. So North America is the first target for us. Of course, there's Europe, Asia, and Middle East, and all these other regions that will also need CO2 capture. And our next, our path forward right now is that we have pilot plants that are operating, and we're working on our next opportunities. So we have opportunities in the cement and lime industry. We have at least 5 opportunities in the natural gas combustion and hydrogen production as well. So we're going to scale up our technology and in all 3 of these regions deploy our CO2 capture technology. I think I'm at time. Thank you very much, and you can contact me for more questions or answers anytime. Thank you.
Great, thanks so much, Brett. I'll be sending links to Brett and Deepika and their emails and LinkedIn after in our follow-up email, along with the slides and the presentation, recording of this webinar. Great, we have a ton of questions. This has engendered a really amazing chat. Brian, you want to kick us off? Do you have one?
There's been a lot of energy in the chat. Thank you for everyone participating. I really appreciate that. And I think one of the themes that we are hearing a lot in the chat is one, definitely resonates with me. I think a lot of us who, as we get our brains around this technology, oftentimes worry that it's just like potentially being used in a way that's an excuse for us to keep doing what we've been doing, is sort of like get out of jail free card. And while we continue to pump fossil fuels out of the earth and don't really apply ourselves to switching to renewable energy. And I know both of you don't agree with that, but you understand the sentiment. So I'd like you to, maybe Deepika, you could start by just addressing that. I saw your answer in the chat, but I think it deserves some conversation because this is an emotional topic for a lot of people. It's really an important question to answer. And I think it's really important to tease out the kind of like the places where it's being applied now as we develop it versus what the plans are for the future and what the big picture has to look like and where this fits in. And I hope you can address that a little bit. Deepika, maybe you could start.
Yeah, no, I completely agree. It's definitely emotional and quite sensitive as a topic. And it's unfortunate that carbon capture as a technology has been sort of initially associated. And again, I want to make sure I'm audible. I know some people said in the chat that I wasn't. Okay, cool.
Good.
I know that's unfortunate that CCS as a technology has just generally been associated with fossil industry, you know, because of its association with coal-fired power plants and enhanced oil recovery. I want to say 2 things. One is, I really don't know if people think that we can wish like fossil fuels away. It still constitutes 85% of the world's primary energy source. So I really just want people to take a second to wrap their heads around this massive situation. And then the other thing is also that we have to, I think I tried to make this point in my presentation of 20 minutes that CCS is not just for energy use, it's also for industrial emissions, which is close to 10% of our global emissions, and we have got to go to zero. So you can't have 10% of your emissions when you're saying you're at zero emissions. So 10% means a lot, and we have got to get those down. And for if nothing else, CCS technologies will be important for those applications. And the other thing I also want to say is that some oil companies now are also trying to use this as an exit strategy. So I heard the CEO of Occidental Petroleum, Vicky Hollab, recently say that in 15 years' time, they expect that they might be making more revenue from carbon management than from making oil, which is a very interesting thought if someone wants to just sort of pay a little bit attention to it, keeping some of our emotions around fossil industries and their misdeeds of the past aside. It's what I would say it sort of represents a little bit of leadership in the industry and in terms of recognizing the transition and the kind of future pathway that these skill sets that these companies have inside. You know, they're high paying jobs. These people who study geology, petroleum engineering, and all these skill sets that we have can be put to use in a totally different way that can serve the climate well. And I think it takes leadership. We're starting to see that. It's not, I would just, I feel like we try to sort of paint everything in one brush, and it's important to sort of understand where different players are sort of taking some steps here. The other thing is also, when I think about coal-fired power plant, I know people get a very, very knee-jerk reaction. I also just want to highlight that if you look at the IEA numbers, there's 43 times more coal-fired power plants in China, India is where I come from, India, China, and Southeast Asia than there are in the US. So it's just, again, another sort of question around understanding the magnitude of the problem.
Deepika, so sorry if I just kind of paraphrase you, but I want to turn this same question over to Brett in just a minute. But I think I hear you saying that, like, first of all, there's a question of scaling and timing, and yes, we're going to scale back our fossil fuel infrastructure. It's going to happen. You're pointing out the question that it might be hard to scale that all the way to zero, but we will reduce our fossil fuel infrastructure, absolutely. But there will be some along the way. If we could pull some carbon out of the atmosphere while we're at it, that would be great. And also, there may be some that it's really difficult to completely get rid of. I think that we have to get our brain around the scenario where there might be some fossil fuels energy generation in our energy mix for decades. So why wouldn't we decarbonize those if they're still going to exist? I don't want to take away from the energy that all of us feel about maximizing the potential to eliminate as many of those sources as possible. We have to focus on that. But I hear you saying, if I'm hearing you right, that yes, we will focus on reducing those, but along the way, we're going to have to eliminate some emissions. And there might be some that are, like, if a coal plant is just being built today, and there are some that are still going in, that thing could be generating emissions for 50 years before it's decommissioned. So what's our plan for that?
And the number that I quoted was plants that are younger than 10 years of age. So you see the kind of emissions we probably already have locked in. I want to remind people there are more than 1 billion people in the world that do not have access to modern energy that we do in the US. And so while we're getting more people access to more energy, you're probably thinking more emissions. And so it's really important to think global, not just in the context of one country. And yes, you captured it, Brian. I think that's it. And we have to get off of these emitting sources. Like, we have got to transition transportation. We have got to transition industry, which is where, and CCS is literally just one piece of the puzzle. Like, it's not everything. We are mostly going to be doing renewables, mostly, but there is a portion of our solution that will come from other technologies, such as carbon capture.
Brett, did you want to add anything to that conversation? I know you have some thoughts about it.
This has been a topic of, had these discussions for 15 years now. Deepika, you brought up something that's interesting, right? Imagine these oil and gas companies have been taking carbon out of the ground, for a long, long time, right? And we've all been benefiting from that, and that carbon has ended up in the atmosphere, right? Now, we can either say no, they can't exist anymore. Those oil and gas companies are bad and everything, or we can think of it as we can utilize those companies to reverse the flow. Right? They have the expertise on geological storage. They have the expertise on carbon being used for plastic production and being used for so many different products. The carbon is coming from the fossil fuel, but imagine now it comes from either the atmosphere or it comes from point source production, right? And really that's the way we're looking at it, is that there's so many companies out there, and a lot of them are oil and gas companies, that can actually transition to helping to reverse the flow. Instead of carbon coming from the ground and going into the atmosphere, it can actually come from the atmosphere or come from flue gas and go into products and go back into the ground, right? The other way around. So that's how we certainly look at that. Now, the other part of making sure that capturing CO2 and the ways that CO2 reduction is actually making a difference is life cycle analysis. There's no doubt that it always has to be looked at properly, right? From a really robust way and standardized ways of making sure that there's CO2 reductions in every project, looking at from before and then after a project and making sure there's CO2 reductions, right? That's standard. That's happening around the world. Those calculations are being put in place, and so it'll ensure that actually every project that we do is actually is truly reducing CO2 reductions. And the third part I'd like to make a comment on is that, you know, we're still relying on products. We're still relying on products. All of us do. So even the people when I have discussions with that, you know, don't agree with carbon capture and they think it's enabling CO2, enabling fossil fuels, they're still relying on concrete. They're still relying on steel. They're still relying on these products where the actual process to get them emits CO2. So there's no doubt that some aspect of reducing CO2 emissions has to be with capturing CO2, or we decide not to use any of those products. Yeah. And I don't hear that, right? I don't hear there being a big push to stop using concrete completely in cities. That's just not happening, right? There's actually growth in those products, not less. So we have to come up with tools and technologies to reduce the CO2 emissions from producing those products. I don't see any other way.
Agreed. You know, as a reminder, people, we are going to be talking specifically about concrete later in the week if you're interested in that topic, because it's a good one, and these two things are really connected. I had one other question, Joe. I know you probably got one here too, but Deepika, you showed a slide that talked about the cost to capture CO2 from different sectors. I was just curious about what your thoughts are. You know, we've all experienced and benefited from the dramatic cost reduction curves that solar and wind have been on over the last decade. Can you talk a little bit to what that looks like in your industry, and hopefully share some good news on that front with us about what the forward-looking costs might be for that removal?
Sure. Yeah. One of the recent studies that was done was on the Petronova project that recently was built in 2017 and it operated for a few years before mothballing. That was a carbon capture application on a coal-fired power plant, 240 megawatts, capturing close to 1 million tons a year. Their study showed that the next project, such a similar project, would cost them close to 35 to 40% less. And a similar study was done also at Boundary Dam, which is also a coal-fired power plant. They did a study for another unit at the same plant, and they also found a similar number that the next project would cost 35% less than the cost of what it was the first time around. So this is a kind of step change we can see literally in one application, because there's a lot of learning. And if you go from one to say fifth of a kind application, you can imagine the kind of cost reductions we can achieve across sectors. And this is really the kind of, you know, story we want to recreate, just like the one that we had for renewables. You know, we had tax credits, so investment tax credits, we had production tax credits for wind. We also at the same time had procurement mandates on the other side of the equation. So utilities must procure a certain percentage from renewables. So there was a way for people that invested in these technologies to actually make money back because they knew they were going to be operating. And that's the kind of support that CCS applications also require. So getting some money for innovation, doing some deployment support through production tax credits, investment tax credits, and at the same time creating some sort of a pull in the market by creating either procurement standards, clean energy standards and such, to sort of create sort of this push and pull effect, so that the deployment goes forward and we take advantage of this kind of learning that we can have. And there's a lot of cost savings that can also occur from sharing of infrastructure. So imagine you have a plant and you have to build your own pipeline and you have to build your own storage site. That's really expensive. But what if you captured your carbon, but also shared the pipeline and the storage site with several others that were going to do the same thing? You kind of share the cost of the storage and transportation infrastructure, which also provides an opportunity to reduce costs and speed up the deployment.
Anything to say to that, Brett?
Yeah, some really good news I'll just point out is that in the last few years, and I would say especially in the last, even in the last 6 months, there's been a huge wave of investment in the CO2 sector. And that is really going to, spawn innovation, right? It has been, that sector has been starved for a long time of mainstream money going into the sector for innovation because there was no clear business model, right? And mainstream money, when there's no clear business model of, they're just not about to give money away, right? They need business models. They need regulatory frameworks to be, robust, like the 45Q. They need that to put the investment in, and that's happening now. So you're going to see an explosion of innovation, and that includes cost reductions on all fronts, right? And that's renewables, that's CO2 utilization, that's CO2 capture, that's all of it, right? And that's what's exciting. That's coming up in the next 5 to 10 years. Is just this explosion of technologies and innovation.
Awesome. I think so. We're 5 minutes over. Maybe we'll do a question or two more, and then we'll see about getting some written questions. We have so many questions out there afterwards. Real quick one: is there an earthquake risk from injecting all the CO2 into the crust?
Brett, do you want to take that? I can just answer simple question. I mean, there are requirements to select sites that do not cause that issue. There's a lot of modeling that is done with a lot of subsurface information that is then used to select the right kind of sites, and we have advanced techniques to do this. That's all I'd say. I don't know if people will believe that, but
yeah, it's been being done for quite some time. There's a lot of data around geological storage. Of course, you don't do geological storage where earthquakes are happening, like the Lower Mainland here in Vancouver. We're not going to do geological storage, but I would say the scientific community, there's so much data around projects that do geological storage that it's becoming a well-known method to do it, right? We know what we need to do. We know what the information we need. We know what formations are needed, and we know how to monitor it. So I think that's coming, right? I mean, that's of course it's always been a question, and but I think that's a valid pathway forward.
There was one other question that someone asked about biomass energy generation with carbon capture and storage. Are you seeing any, for people out there, the reason why that's interesting is because potentially, if you imagine you're growing biomass, which accumulates carbon, then you burn it for energy and pull that carbon back out of the flue and store it. Basically, that's a negative emissions model, and you're getting energy out of it. So it's quite intriguing that way. Are you guys seeing signs of development of those kinds of solutions anywhere?
Absolutely, we see the pull for that fuel switching happening, especially in Europe. And they can reduce CO2 even so much more by switching fuels and then doing carbon capture on that project, right? It makes a lot of sense. And in Europe right now, the waste to heat is being done everywhere in Europe, right? Not so much in North America yet. We got some work to do on that, but in America, waste to heat is a common thing already. So if you capture the CO2 from a waste heat project, then you can actually do negative emissions. So I think it's a fantastic pathway. There's only so much biomass in the world, so it doesn't solve everything, but where it can happen, why wouldn't we do that?
Fantastic. Well, I think we're about 10 minutes over, and I want to be respectful of everybody's time. We will send along the chat and all the questions, and we'll see if our panelists have any time to help answer any other ones. And we'll send a follow-up, this video and their slides as well. I want to remind everybody they can sign up for the rest of this Sequestration Week's webinars. I just put the link in the chat again. Thank you to Deepika and Brett so much for your expertise and your work. We would love to have you back in a year or two and see where things are. I'm sure this industry will change a ton in the meantime. So thanks to everybody. Happy Sequestration Week. Hope to see you tomorrow for our webinar on forests. And we'll talk to you soon. Thanks.
Thanks, everyone.